outside the blast radius, explosive discovery unburdened by knowledge. So really excited about this speaker today because it's a little different than the normal speakers that we've been having. So it's going to be a little different for our chemistry and researchers today. That we normally, it's all been directed towards you guys. So really excited about this one. So anyways, I'm going to let Pat introduce our speaker. And again, thanks for coming today, guys.
All right. We're good? All right. So, like I said, we're super excited to welcome Professor Matzger as our next distinguished speaker. Professor Matzger received his BA in 1992 from Oberlin College. His Ph.D. was completed at the University of California at Berkeley in the group of Peter Vollhardt. He went on to postdoc jointly with Nathan Lewis and Bob Grubbs at California Institute of Technology. In 2000, he joined the faculty at the University of Michigan at Ann Arbor, where he's now the Charles G. Overberger, Collegiate Professor of Chemistry, and the Professor of Macromolecular Science and Engineering. His current research interest focuses on organic materials in solid state and encompasses explosives, pharmaceuticals, and porous materials. And with that, I'll turn it over to you. Thank you so much.
Okay, well, thank you, and thanks for the opportunity to visit here. This is a place I've sent many people to, as you know, to get some experience in the real world. That is what you guys are dealing with every day, to free them from our academic stuff for a while. But what I'm going to tell you about is the very academic side of this, and how, you know, I came into energetic materials and some of the things that you know, we've thought about as sort of outsiders in the field. All right, so I'm going to take you back to 2005. Okay, so 2005, Hurricane Katrina, not so pleasant, but we have the Xbox 360 launching. YouTube is founded. And in fact, if you think about why you never hear of these guys, because the next year they sold it to Google for $1.2 billion, so they're probably off on their own private islands. Another thing in 2005 from popular culture here is Harry Potter and the Goblet of Fire. And this is extremely relevant because if you look at the tagline, it's everything is about to change. And indeed, in 2005, everything was about to change for me. So what was I doing in 2005? So I was a plucky assistant professor, just going through tenure at that time. And what I was doing was crystal polymorphism. And I was studying pharmaceuticals and the ability of those pharmaceuticals to pack in multiple ways, and that's how that can affect their bioavailability, this problem in crystallization. And we had been pretty successful in taking things that had been known for many years, like this sulfamethoxazole, and then applying our own techniques to find forms and be able to find additional polymorphs. And also, this was a kind of exciting time for pharmaceutical polymorphism. There had just been a case where Abbott Labs had launched a drug called ritonavir, and they had launched it in an unstable form. They didn't know that, and it transformed to a more stable, poorly bioavailable form in all their manufacturing facilities. So this was becoming a pretty exciting topic, and it cost them about $500 million to fix this problem. So one of the things we had introduced was we started out with commercial polymers, and we started using combinatorial methods to make libraries of copolymers, and then use these copolymers as surfaces for the heteronucleation of crystallization. So when you have molecules in solution and they're ready to form crystals, there are kind of two ways that this can happen. The classical way we describe it as what is called homogeneous nucleation. The molecules aggregate, they grow larger and larger until you get to a critical size where the energy continues to go down during the process. And this is what is called homogeneous nucleation. And it's fairly rare actually in lab scale. What is much more common is to get heterogeneous nucleation. Some impurities, the sides of your flask, whatever, lower the barrier to crystallization. And so what we were doing in the research at that time was exploiting that fact that heteronucleation was ubiquitous, and we were just providing libraries of hundreds of different nuclei on which to grow crystals. And so we would take, we would grow in 96-well plates, a bunch of cross-linked polymers, and then we'd look at, for something like acetaminophen, how does that allow us to select among the forms of acetaminophen? And what this looks like is we have these clear polymers in the background, and then we grow selectively either the monoclinic or orthorhombic forms of acetaminophen, and these polymers were allowing us to address many more systems than we had done in the past. Okay, so now 2005, I get invited to give a talk at in a section of the American Chemical Society I'd never even heard of, called Chemistry and the Law. And here's my abstract. So I was going to talk about crystal polymorphism in pharmaceuticals, fundamentals of discovery and characterization. So I talked all about the fundamentals of this and was telling lawyers, because this was becoming a very hot area in litigation, and it's still a very hot area in litigation. And the reason for this, you might think that, a drug like ritonavir or something, well, the pharmaceutical company, they have the patent on that, so nobody can sell it. Well, they have the patent on the chemical structure, but normally it's later during the development process that they find the solid form, the polymorph, that they are going to deliver to the patient. So it's very typical in pharmaceuticals that the only thing stopping a generic from entering the market is a solid form patent on whatever it is you're selling. So this was becoming a hot thing for people to understand, and there were a lot of cases, and now it's just typical, there'll be a couple of billion-dollar cases a year around solid form patents. So anyway, that's what I was there to talk to them about, and I talked about sulfamethoxazole, and I talked about carbamazepine, which we had just, we'd found a fourth polymorph of, and I was really excited about that and telling them about highly polymorphic compounds, this idea you could have 4 different forms, which was about as many as you could get at that time. And so I get back to Michigan, and I get an email from somebody at China Lake, Bob Chapman. And I'll summarize. Bob's email was basically like, I know you think your pharmaceuticals are good, but energetics are really polymorphic, so you should be looking at those. And he, in particular, pointed out 2 compounds, CL20 and HMX, that he said had 4 polymorphic forms, and that would match what were sort of the highest, polymorphism compounds at the time. And so we went back and forth. We had, many emails back and forth about this topic. And I told him, well, polymorphs, they have to have the same composition. So if you have a hydrate and a non-hydrate, that's not really a polymorph. So HMX really has 3 true polymorphs and then a hydrate, and CL20, the same story. It's got 3 polymorphs and then a hydrated form. And he said, okay, well, that's fine, but maybe what you should work on is HNFX. So at the time, there was this compound, HNFX, and he had been involved in the synthesis of this, that only had 1 known form. And you compare that to something like HMX, which has, these, depending on the, how you count the polymorphs, hydrates, and certainly at least 3 unsolvated forms, and like 90 adducts, with solvents, and then you have something like HNFX that just has 1 solid form. So he said maybe you could apply some of your methods to HNFX and then see if you could get another form of that. And I just want to show you kind of before going on talk about the landscape of HNFX. Here is just an example of the true polymorphs of HMX. And in terms of, so what is it that makes something a polymorph? Well, you can have different conformations. So we can see we have different conformations of molecules between beta HMX and the alpha HMX. But then it's not just the conformation, it's also the way these things ultimately pack into the crystal that makes things polymorphic. And from a practical standpoint, for people that are going to use these things, the implications are significant. Density, which is tied to performance, varies between polymorphs. Impact sensitivity, friction sensitivity, all of these things matter, which actually explained why so much beautiful work had been done trying to exhaustively elucidate the polymorphism of energetic materials. And because of these different conformations and different packing, it means we have different spectroscopic signatures as well. So here, for example, are polymorphs of HMX and then one hydrate. And there are, differences in characteristic regions, and we can use that, therefore, to identify the result of a crystallization. So we applied this first. We began, so our first question was, he said, you could talk to this guy, Judah Goldwasser, at the Navy, and maybe he'd give you a grant to look at HNFX. And things like, can you work with explosives and receive explosives? I said, sure. So they sent him over because it was a different time. It was 2005. Now you can't do that. But we got these things, and so I started looking at these large libraries of polymers and growing by heteronucleation on these polymers, different polymorphs of HMX. And indeed, you can selectively get the alpha, beta, or gamma. Now, those were all known, but the way they're typically made is by varying the solvent or the temperature, or sometimes there are kinetic conversions that can occur. So here we're doing all of this discovery from one solvent under one condition, just evaporation. And sometimes you would get mixtures of forms. You might get, even all four, but you could also find with some of these giving us selective heteronucleation of one form over all others. Okay, so that's the warm-up act. So now we need to apply this to HNFX. And so here is the crystal structure of HNFX. The crystal structure is correct. It's been determined a couple of times by us and by other people. And it has a property you don't see very often in organic molecules, which it's got a hole in the center. And in fact, this hole is big enough you could put hydrogen in there. We've done hydrogen absorption measurements, and you can stuff that into there. So this is just happening to crystallize in sort of a unfortunate, from an energetic standpoint, manner where it has some porosity in the structure, and so it gives us a density that, while okay, is nowhere near what it should be predicted from the structure. So what is predicted? So here is the polymorph predictions for HNFX, and you can see this is basically the known one, and then there are a whole bunch of others that are predicted to have densities about 0.2 better. And not only that, they're predicted to be more stable, some of them. We were never able to get anything except that one polymorph of HNFX that has a density that is too low for it to be usable. So this led to a pretty straightforward question, which is, well, what do you do when polymorphism fails? What are your options for improving the property of a material? And so what's done in pharmaceuticals, and what we ultimately end up applying here to energetic materials, is to make solvates, for example, or to make co-crystals. The conceptual difference between a solvate and a co-crystal is nothing. The practical difference is solvates have things that are liquids at room temperature, and co-crystals are crystals where you have two components, but they're both solids at room temperature. So then the dream was that we were going to take this two materials, ultimately an energetic material A and an energetic material B. Maybe one of those has a problem like low density, such as HNFX. And maybe another one has a problem like high impact sensitivity, like Cl20. And then we're going to co-crystallize them, and we're going to get something that is going to have novel properties. Now, those properties may be worse, or they may be better, but at least you've got a shot that you've modified the properties of this. And you can do things like for the oxygen balance, you can trivially compute that. But for all the other properties, impact sensitivity, the density, this is going to require some experimental testing. So the idea ultimately is to improve handling and power, and I'll show you examples of all of these in some of the cases that we've studied in my lab. Okay, but before you can run, you must walk. So we needed to first show that we could actually make some co-crystals. And so we begin with TNT. TNT, we were able to make co-crystals with all of these compounds. And I'll just give you the gist of what these look like. So here is crystal structure of one of the polymorphs of TNT. We then crystallize it with anthracene. You can use naphthalene, whatever you like. And you get now this pi stacking interaction with alternating anthracene and TNT. And this is actually totally expected. And it can be predicted from the electrostatic potentials of these molecules. So TNT, because of those three nitro groups, it's drawing electron density out of the pi cloud, and so it's making that electron deficient, whereas naphthalene, we have this nice electron-rich pi region, and so when those come together, we get pi stacking in the solid state. And indeed, for all of these successful cases, you can see a similar pattern. They all have an electron-rich, electron-poor, what you call a donor-acceptor type behavior that is favorable for co-crystallization. So now with this basis that we could start looking at properties and see what kinds of properties we were getting. And so I've shown here the co-crystal density and then the co-former density. And you can see TNT already, orthorhombic and monoclinic TNT, they're way up here, pretty, reasonably dense. But we did find a few cases here at the edge, like with bromonaphthalene and with tetrathiafulvalene, which is a very electron-rich molecule, where we were able to make something more dense than either of the two things that went into that co-crystal. And we thought, well, now that's pretty interesting. We're not always getting an averaging of properties. We might get new properties emerging. All right, so then we went on and we started looking at, we couldn't really apply this exact design principle to energetic materials because most of those do not have an electron-rich pi face to undergo this type of reaction. But it's okay, we can screen and hope. And that's what we did. And this was our first hit, and really the first energetic co-crystal. And this is a one-to-one co-crystal between Cl20 and TNT. And there certainly are some of the interactions that look like they're consistent with electrostatic interactions. The morphology of this is actually very nice. And the density of the co-crystal was considerably better than TNT, better even than gamma Cl20, but not as good as the other forms of Cl20 in terms of just the total density. But, maybe there's some other interesting things about this, because you've taken something expensive and impact sensitive and you've cut it with something cheap and non-impact sensitive. So maybe that would give us some angles. And so what we found is that the impact sensitivity, it requires about twice the drop height to set off this Cl20 TNT co-crystal as it does to set off epsilon Cl20. So we made it less powerful, but we've also made it less sensitive. But the thing that was a little more interesting here is if you heat it, it exudes liquid TNT, because TNT is relatively low melting. And what it leaves behind is a more sensitive form of Cl20. And so now the impact sensitivity of this, it's now more sensitive than Cl20 or the co-crystal. So we thought, well, you could maybe ship it in that less sensitive form, and then you could activate it to a more sensitive form. All right, and so this is a new energetic material. It is a new energetic material made with two energetic materials for which there is already existing knowledge and infrastructure. And so the advantage of that is, like, the year after we publish this is being scaled up in pounds, and they're doing large-scale sensitivity testing on this. This is a very difficult thing to do if you make a totally new energetic material chemically. But supramolecularly, this is a good way to go. The next really exciting energetic co-crystal that we made was Cl20HMX. Now you're seeing an effect of stoichiometry. There are actually 2 Cl20s for every 1 HMX here. And so this is the crystal structure shown here and here. So a little bit of disorder. Again, the morphology is pretty nice. Now, of course, when we were doing this, we thought Cl20 wasn't as much interest as it is today, right? Cl20 is getting more interesting. And so, this is a pretty, I think, interesting co-crystal as well. And it has been scaled up in flow by the Klopotka group, and probably others that I don't know about. So here is the density for the 2-to-1 Cl20 HMX co-crystal. You can see higher than all of the HMX forms, but still falling a bit short of epsilon Cl20. So then we can calculate also its detonation velocity using Cheetah, and we find now that actually is looking quite good in terms of you're getting substantially better than HMX, but it's only going to matter if you've done something about impact sensitivity. And it turns out that that is a pretty good story as well. So when we do drop testing, this 2-to-1 Cl20 HMX is not inheriting the sensitivity of epsilon Cl20. Instead, the sensitivity is like that of beta HMX. So hopefully now, with more interest in Cl20, we'll be able to see this, scaled up further, and instead of having, our small-scale impact sensitivity, we'll have a more legitimate force, look at some of these things. Okay, so we've given up a little bit of performance, and we've gained considerably in impact sensitivity. So what about if we want to push things even farther? We want to go to exceed the performance of Cl20. So to do that, we got inspiration from alpha Cl20, which is a hydrate. And so we know the crystal structure of alpha Cl20 has waters in the crystal structure, and these waters do us no favors. The waters have no energetic content. They take up space in the crystal, so they rob you of density. There's really nothing to recommend them. But we thought, you know what looks kind of like water? Hydrogen peroxide. Maybe we could, get that in there? So that was our thought experiment. And then we were able to actually we got some. So first we started making it, and then we found we could actually get 98% hydrogen peroxide. And so this should improve the oxygen balance and certainly should improve the density of the solvate as well. So we did a lot of our initial screening with Raman spectroscopy, and we could see that when we were growing this out of hydrogen peroxide, we were seeing changes out here, consistent with changes in hydrogen bonding patterns. But also, with peroxide, you have a OO stretch that's down around 880, and we were seeing that as well, that was occurring in the potential hydrogen peroxide solvate, but not in the alpha Cl20. So it looked pretty good, and so we were able to crystallize this. And here are crystal structures, and we got more than we wanted. We got 2 polymorphs of the solvate, and one of those has a density of 2.033 at room temperature. The other one also has a pretty respectable density. And if we look at what's going on, there's hydrogen bonding interactions between the nitro group, not the best hydrogen bond acceptors, but peroxide is a pretty good hydrogen bond donor, and so it is willing to make this solvated form. Okay, so what does it do to our impact sensitivity? That's our first question. Well, the impact sensitivity does, get maybe a little bit. It's going to be more powerful. We have hydrogen peroxide in there, and indeed, relative to epsilon Cl20, it's now a little bit more sensitive, much more sensitive than the 2-to-1 Cl20 HMX crystal I was telling you about. But then we can look at our performance projections with Cheetah, and we can see that for the more dense form, we are predicting substantial increases in detonation velocity and detonation pressure. This has been scaled. Student John Bennion, who's now at the Army, he went to Purdue, and they made 5 grams of this and then did detonation velocity measurements on this. It's pretty stable. We've had it around for quite a while. I don't know that I'd want to bake it on the deck of an aircraft carrier, but it is, a relatively stable solvate. All right, so I want to tell you about just a few other things that we looked at, and I think this really shows our novice status. We thought we'd work with cyanuric triazide. It can be made in one step. We didn't quite know how energetic it was and how sensitive it was. Fairly, it turns out. We thought that this would be a great compound if we could desensitize it a bit, because it could act as a primary that might be metal-free. And so we took it with BTF, and these are both actually fairly electrostatically neutral. There's not like a donor-acceptor interaction here that is clear to see, but this is fairly electron deficient, and we actually do have some electron donation from these nitrogens. And fortunately, it does co-crystallize, so we're able to make 2 of these cyanuric triazides to BTF, and we get a crystal structure of it. And then the question is, all right, so could this potentially be a primary? Have we made our properties better or worse? So one thing is the impact sensitivity. It is in the primary range, a little bit more sensitive than PE10. but much less sensitive than cyanuric triazide itself, and it hasn't shown any spontaneous detonation, unlike what can be said for CTA. It is one of the reasons CTA is also not very popular in energetic materials is it's volatile, so it can tend to move around in your formulation. So we looked at the thermogravimetric analysis, and you can see that CTA sublimes very easily. We get a little bit less of the in the co-crystal. So the co-crystal is more stable, so it suppresses the vapor pressure of the CTA. And in fact, we can look at that quantitatively, and you can see at different temperatures, this is the suppression of the CTA vapor pressure that you get at each of those temperatures. So at 85 degrees, you're already down, at about a 7.5 decrease times less volatile. Also, it changes the thermal properties. So here's the DSC. The co-crystal melts actually at a higher temperature than CTA, and so we got quite a few changes in the properties there as well. All right, so we've done a lot of stuff with neutrals, and we got really interested in the problem of propulsion, and in particular perchlorate replacements. So ammonium perchlorate is obviously widely used, but has some problems. And so I had a plucky graduate student, Michael Bellis, who decided to attack. He used to be plucky. Said, I'll work on this problem, and in particular, take a look at ammonium dinitramide and see if that's something we could co-crystallize to improve its properties. Ammonium dinitramide looks great, except for all its properties. So it's hygroscopic. It just turns into a puddle. It makes horrendous needles that nobody wants to try to pack into munition. And it's also quite thermally unstable and undergoes autocatalytic decomposition. So it doesn't have much going for it in its own form, but it's got a good oxygen balance, 25.8%. Environmentally, it looks better than perchlorate. So there are reasons, if you could tame it a bit and change its morphology and hygroscopicity, that maybe this would be a good compound to look at. So this was really the first time that we were going to apply co-crystallization to a salt. And so what worked out very well was this pyrazine bis N oxide. So we predicted that this would be a good hydrogen bond acceptor from the ammonium that would allow us to co-crystallize ammonium dinitramide. And indeed, this worked out really well, and it got us actually thinking in all kinds of new ways, because we were finding that basically this looks very much like the salt here, and then it looks like your coformers in between. And so this led us to a whole bunch of things I won't talk about today about lamellar architectures in salt co-crystals. The morphology was great. The oxygen balance, CO oxygen balance, was 0. And the melt temperature and decomposition were raised by a bit in this material as well. All right, so that's sort of the deep dive in the co-crystal. So we got here, right, polymorphism failed us, and so then we needed to start looking at co-crystals, and then we found a lot of different things co-crystals can do. I'm also going to mention 2 other things you can do with co-crystals that we sort of weren't even contemplating at the beginning. So one of these is you can make something not melt castable. So the ADNP is not melt castable, DAF is. The co-crystal can be melt cast and it will reform as the co-crystal. And what's happening is in the melt of the co-crystal, shown here, you're actually suppressing the decomposition of ADNP, because the solution state, what's coordinating to that ADNP, matters in its stability. So that gives you enough of a window that you can actually have that stuff in the melt, recrystallize it, and get back the co-crystal. And then Andrew Bennett, who I think a number of you know, came here with NREP. He got trained by and built on a lot of Mike's work, and found that you could make ammonium nitrate and ammonium dinitramide co-crystals of DAF. No, sorry, that is DNBT. And now we're into the point where we're having positive, CO positive co-crystals. So we've able to, what we had done before, we had energetic oxidizing salts, we could turn them into explosives. Here we have excess oxidizing capacity as we, in the co-crystal. So co-crystallization is great, but it's not perfect. It fails. It fails a lot. And I'm not telling you about the TNT HMX co-crystal or the RDX Cl20 co-crystal, because none of those exist, and they may never exist. There's no reason that things need to co-crystallize, because they've got a great alternative. Unlike a salt, they can just form a physical mixture of the pure A and the pure B. So what do you do if you have something that doesn't want to co-crystallize? What can you do to force those things together? And so for that, we turn to metal organic frameworks. And so metal organic frameworks, very current topic, since it was the 2025 Nobel Prize, have found all kinds of applications in gas storage, in catalysis, separations, drug delivery. And there are actually a number of MOFs that have been used with energetic linkers that are explosives. Most of them are not porous, though. I guess none of them are porous, at least permanently. So we thought if we used a porous MOF, what you can do is you could take that MOF and, through a process called activation, remove all the guests out of the pores. And then that MOF is very hungry for anything to go into those pores. So unlike co-crystallization, where it's happy to form pure A and pure B, there is a strong driving force for things to enter that MOF. And that's what we were going to do. And we're going to start with these kinds of porous MOFs. And here is our vision for how we could make on-demand energetic nanocomposites. So we can choose the metal. The metal is going to give us, that's our structural linkage, but also it can catalyze various reactions, such as perchlorate decomposition. We're going to stuff an oxidizer into this, and then we can modify the organic linker. And using all of this, we have a lot of knobs to turn to make a custom energetic material. And I want to talk a bit, just a speck about length scales. So when I think about length scales in energetic materials, you think about composite solid propellants, where you have, microns, hundreds of microns between oxidizer and fuel in some cases, between your aluminum or your HTPB and your ammonium perchlorate. An explosive, you can think of that as, it's a molecularly bound composite, right? And the length scales are very short. We're talking angstroms, which is why you get super fast reaction rates when this nitro goes to oxidize this methylene, whereas when you try to get AP to oxidize the butadiene, it's a much slower reaction. So where do MOFs lie on this length scale? So I'll show you a picture from tetranitromethane. This is a model in the crystal structure of MOF5. And the distances that we're talking about here are about a nanometer. So it's actually very close mixing, similar to what you get in a molecular species. So we expect fast reaction rates. All right, so the system I'm going to tell you about uses a MOF called MOF 74. We'll talk a little bit more about that in a second. And we're going to use lithium perchlorate. Why lithium perchlorate? Because it's got a superb oxygen balance. It's 60%, plus 60% oxygen balance. And so then we're going to melt, infiltrate this, and we're going to use the organic linker as the fuel for this oxidizer, and then get this thing hopefully to detonate. And the idea was also to pick the metal judiciously, something that could catalyze perchlorate decomposition, because while lithium perchlorate oxidizes, it does so at about 500 degrees. So here's what this looks like. This is a Raman spectroscopy map of the physical mixture of the MOF, which is in red, and then the green oxidizer. And this actually looks very similar to a composite propellant in terms of the length scales of mixing. But now we're going to melt it so that all the green stuff gets sucked up by the red stuff and now becomes mixed at the nanometer level. And here's what this looks like. So here's lithium perchlorate, DSC, melt, then much, much later you get oxygen evolution. When we do this in the presence of this magnesium-based MOF, we get a little melt, but then very quickly you see an exotherm. That's not decomposition, it's adsorption. Because that MOF is empty, there's a strong driving force for things to go into those pores and for adsorption to occur. Then a little bit later, yes, it does detonate. Now, if we do this with the nickel compound, very different story. Now it melts and explodes. And that is because nickel is a much better catalyst for perchlorate decomposition than is magnesium. So that oxygen becomes available right after the melting of the lithium perchlorate, starts oxidizing the framework, and the whole thing runs away. So we can look at this by thermogravimetric analysis, and we can look at the heat evolution, and we find, this kind of, this is, the signature that you need to go retrieve your TGA pan from the furnace because your stuff's blown up and it, came off the hook. And so that's what happens when we do it with nickel. With magnesium is the loose powder, you're okay, and then lithium perchlorate, just straight oxygen. We do this in sealed pans, and we can see there's actually more heat evolution and earlier from the nickel MOF than the magnesium MOF. So that was interesting. We also looked at gas evolution. We find that we're getting more gas evolution in the presence of the nickel catalyst than the magnesium as a structural metal. And so we've done that. We've published on that. Now, what's much more recent, we just published, I think, this year, is changing the organic linker. So the organic linker is the source of our fuel, but not just the source of our fuel. We can also use that to control the pore size. By using a longer linker, we can make these pores, let's say, 2 nanometers, and that allows us to put more oxidizer in. So let's look at how that affects things like the oxygen balance. So if we add 1.5 nanometer pores when we use this linker, we're up to 2.2 nanometer pores when we use this extended linker. And we can structure them both with our catalytic nickel and then see how that's going to affect their properties. And I think I'm going to just skip ahead to show you the effect, because I think I probably only have about 10 minutes. Is that right? Yeah. Okay, so here is when we take different weight percentages of lithium perchlorate and we mix them with that MOF, and then we look at the heat release by DSC. And we find that that maximum heat release goes up in the larger pore MOF, and it's shifted to a higher loading of the oxidizer. And by DSC, we can see more heat is being given up. A lot of this is because the metal is kind of dead weight. It's not giving us a lot of heat in this reaction. So then we said, well, okay, let's push this even farther. Let's get let's get some hydrogen out of our linker. Let's extend that linker and let's get more energy in. And nothing excels at energy in the organic world besides nitros is alkynes. I mean, acetylene itself is unstable relative to the elements. So you're starting up here, and that's always a good thing. So we made this linker 3 nanometer pores, and now we are finding that we should be able to load up to make even positive oxygen balances in this case. And so we then do that whole series of measurements, and we find indeed we can get up to 67 weight percent of lithium perchlorate is giving us our maximum heat release, and that heat release is substantially higher than these other metal organic frameworks, so this is starting to be actually pretty good. We're also generating a lot of gas here, but I'll show you something that is maybe pretty surprising, which is from the TGA. This also shows up in the DSC. The highest performing composite, the one with the energetic linkers, is actually the most stable. So it goes off at a higher temperature by DSC and by TGA. Now, one possible reason, it does have a lower nickel content, so it could be that we have less catalyst, but there could be some other reasons too. It's the one that gives us also the greatest gas generation. Okay, but let's see if these movies will play. All right, so that's the nickel MOF74 physical mixture. Here's the now more extended, and then this is the diine super extended one. So even visually, you can see a big difference when these things go off by high-speed video. But again, the thermal stability, you don't normally get higher performance and higher thermal stability, but here you do. Okay, so what about other measures of sensitivity? Well, we can do drop impact, and we use the maximum height of our apparatus. It doesn't go off. We don't have one of these fancy electrostatic dischargers, but we have a Tesla coil. So the composite's totally insensitive to impact and to electrostatic discharge. And this is because that mixing is on the sort of 25, 50 micron level until you melt this stuff and you get that melt infiltration. And then things become very sensitive. Okay, so then the last thing I want to tell you about, something unpublished, and that hopefully is pretty exciting. And I want to talk about this problem of balancing sensitivity and performance in the context of conventional energetic materials. So we take something like HMX, we can formulate it to make it less sensitive in a polymer bonded explosive, but you can go too far. I mean, you lose performance, but you can have things fail also to go off. So there's always this question about sensitivity versus performance, and is that something you could address through switchability? And so the idea I'm going to tell you about is to use photo switching of components within a formulation to change the sensitivity of an energetic material. We've just been working on this for a year, and so we don't have anything published yet. So this isomerization is very reversible in solution between a benzospiropyran and a myrocyanine. And the reason we thought this was kind of interesting is, though predicting the sensitivity of energetic materials is tough, one of the models people look at is electrostatic potentials. And so we thought if we could get something like this zwitterion that would really mess up the electrostatic potential of the energetic, maybe that could make it more sensitive. And this is commercially available, but it doesn't isomerize in the solid state. We couldn't really coat it on energetics well. So we just made a simple derivative. We just added some grease, make it more soluble to impede the crystallization. And then we coated that with slurry coating onto HMX. And we found that we could take HMX, we desensitize it a little bit if we put some of this stuff on, and then we can sensitize it again by exposing it to light. So we then we found that was not reversible in that system. So we found a system that was reversible, which is shown here. And you can see the reversibility. Here it is it will revert on its own. So let's say, you go somewhere with your energetics and somebody says, hey, get ready to, use this energetic. So you irradiate it, you sensitize it, and then they change their mind. They're like, oh, we have a deal, we're going to head back. Okay, so then this stuff will revert from this more sensitive state to this less sensitive state over time. But you can also do it with light. So here is what it looks like when we coat this stuff. This is not a false color matte. This is actually when we irradiate this stuff, it turns purple. So let me show you a little video of this. So I just have two piles of the same material. It's HMX coated with this particular material. I'm just going to cover it with the light, and then I hit it with 365. This is real time. It changes like that in a second or two. Now I'm using white light, and a few seconds later, maybe a little more, it's a little slower, it's back. So you can cause this stuff to go from the sensitive state to the insensitive state pretty well. Cover it again, can do it again. Again, it's very fast. We have a ball doing this in lab, back and forth, as you can imagine. Okay. So here is the sensitivity for RDX and HMX. I think I'll just move on to the main event. So now we've done it in polymer bonded explosives. And we find we can put 1% of this in a polymer bonded explosive, this spiropyran, and we can sensitize it and we can revert it. It seems to be, it's pretty compatible with cure chemistries that are used for HTPB. And there's a lot of questions remaining, but it's something that we have been having a lot of fun with. And so we're trying to get actually the levels lower, working on issues of light penetration, improving reversibility, and the robustness of the effect. There's a lot of knobs we have to turn here. I think I will stay on time. And I want to thank, this is sort of, over time, ONR got me started in this area and has continued to fund our work in co-crystallization. DITRA was really helpful for a while, and the Army and the Air Force as well. And actually that last stuff I showed you, the unpublished stuff, that's been a new DARPA project. And then here are the main students sort of in order of time for when they contributed to these projects. I tried to talk about each of them and shown their work on each of these slides. And yeah, so it's been 20 years now, and so I don't know if I'm still outside the blast radius, but I still don't know as much as most of my students about real energetic stuff. And also thanks a lot to Antec and Layla, two more senior scientists in the group that also help keep things going. There's Andrew Bennett, but nobody else from this. Oh, Julia, so she worked on the DARPA stuff. All right, I'd be happy to answer any questions. Yeah, Jeff?
One gets similar activities replacing a carboxylate with a 5-substituted tetrazole. Does that work with metal organic frameworks?
Yes, there are certainly cases. The chemistry's a little harder. So some of the early stuff we did were called zeolitic imidazolate frameworks. So they're high nitrogen linkers that can go. Yes, it's certainly a way to start a little bit higher in energy. So far, those with energetic linkers have not yielded porous materials where you're then able to load more stuff into there, but I wouldn't give up. I think it should work. It's just the chemistry's not as nicely reversible as the carboxylate chemistry. But yes.
Hey there. Just a question on the reversibility that you were investigating. How many cycles have you gone out to, and have you looked at like changing safety properties over time? Like kind of doing like a mini...
for those Zwitter ion stuff?
Yeah, like kind of a mini aging study almost.
Yeah, I mean, we haven't really looked. I mean, there are a lot of things that are photochromic over a gazillion cycles. I mean, your rear view mirror in your car that dims, transitions glasses, all of these kinds of things use related chemistries to this. This is pretty well established reversible reaction, but in a composite, there are other things to worry about. We have seen reactions if we don't do things just right in the cure agents. If we use high temperature cure, it'll go purple and not go back. So there are definitely those considerations. Yeah.
You have any thoughts on why after I believe it's a CL20 TNT co-crystal, why after the TNT has been removed up from melting, why the remaining CL20 has more sensitivity?
I think it's epsilon CL20. No. It's a different form. Okay. So it's not actually the most stable form of CL20 that comes out of the melt extrusion. I think that's why it's more sensitive. Yeah. CL20, by the way, is special for co-crystallization. It has yielded many, many co-crystals, so that's good.
Has anyone looked at polymorph synthesis using selective irradiation of Raman frequencies or microwave frequencies unique to one polymorph to encourage crystallization of the other?
I don't think so, but I think it's a great idea. If you can get enough power in, because the idea would be to stop it at the nucleation phase, right? And so as long as you could get enough power in and you had enough separation between those bands, I don't know how narrow you can go. You need a tunable, very narrow band IR laser, but I think such things exist. Lasers get better and better.
Heating only the thing we don't want, and everything else would be transparent.
Yeah, I love the idea.
Sounds beautiful. What could go wrong?
You're a co-author if we do it. If somebody already did it, I'll let you know.
So going back to the beginning of the talk, I'm curious how it works with the heterogeneous nuclearity. So are these elastomeric polymers? Are they hard polymers?
These are rigid cross-linked polymers. We heavily cross-link them because we want to be able to use solvents like DMSO or, we want to be able to use any solvent. And the only way to guarantee compatibility is by heavily cross-linking these materials. Yeah.
And so what are the physics behind the crystallization? Is it, so it's crystallizing on the surface of these polymers?
Yeah, I mean, so the basic reason why heteronucleation is, right, so this is our nucleus in solution, and it's not as stable as the bulk crystal because it's got all of this surface energy, right? All of these unsatisfied valences on this sort of 3-5 nanometer crystal, right? So if that can have one surface interacting with a heterogeneous nucleation, that's why the process is quicker. It's basically always going to be advantageous because that's going to be a lower energy. So then you just need to provide it that and not, basically a library of those and slow down homogeneous nucleation, which we have things to do. Filter your solutions, get rid of other heterogeneous, nucleants.
And then for the MOF work, what's your use case? So you talked about maybe you would actually ship it where you've got this heterogeneous material, and then you think you would actually heat it before, the actual energetic event? Or do you have any concepts of ways that you might be able to make just a stable MOF where it's already in the pores?
Yeah, so I mean, that's what we're working on right now, but I think if it's in the pores already, I think you're going to have sensitivity. And so the thing that I think is really special about this is the ability to have it be super insensitive, and then just when it gets hot enough, it becomes sensitive. Whether there's a use case for that, any one of you would have a better opinion than I would.
Hello, thank you for the talk. I'm not familiar with this field at all, so I have just like a novice question. But you mentioned for one of the crystals that you worked with, it had a low density and a large pocket.
Yeah.
And I'm wondering why that's a bad thing. Is it because it's dead space, or does it have a destructive effect, or why is that bad?
Okay, so I'll tell you a story. I was at my first Navy review, and everybody was talking about density. All they could talk about was density. And I was like an outsider. Why does everybody care so much about density? And so I turned to one of them and said, what is this? Because, lead's very dense, and it's not very energetic. And what the guy said to me is, yeah, but lead azide is. And that's when I realized the thinking in the field around density is everything, because by having all that energy in a smaller space, first you can get more payload there, but then the pressures you can generate, the detonation velocity all increases. So there are no energetic materials that are successful that have densities around hexane or, other organic things. It's always got to be, people poo-poo TNT because it's only 1.7. People want 2 or, 1.9 at least. And it's just very important to get that power packed as small as you can.
Hi, I just had a couple of questions about the Zwitterion work. Yeah. First off, do you know how well the UV light can penetrate through the material? Like, imagine if you had like a bulk amount, would it only activate on the surface and not in the interior? Or
yeah, so this is something we're worrying about a lot. So there were measurements in the literature for the UV light penetration through RDX, HMX, all of that. Fortunately, they were all wrong. They were all based on scattering. So you can actually, the practical, you can get through about a couple of millimeters, okay, of energetic. Now, once you put the Zwitterion on, of course, you could have too much absorbance. That's why we're trying to get the loading down even further so we can get more. However, for impact sensitivity, having just the outside of whatever is being impacted sensitive is not actually a bad thing. It saves you photons, and you can get sensitization where the impact is going to occur. So it may not actually be so desirable to have transformation through the whole munition.
And then my other question, so it's activated with UV light and then deactivated with visible light, right?
Yes.
So would you need to use just visible light to deactivate it, or if you left it out, because sunlight has UV and visible, right? Would you end up with a mixture of the two if you just left it out, or?
Yeah. So I'm not. You mean in sunlight? I don't know. We know there's a thermal reversion path, so at least for some of these, but it's going to vary a lot depending on the system, because it actually turns out the switching is occurring within the amorphous regions of the material, and the crystalline material isn't even converting, is what we think right now. So it's going to be complicated, and ultimately I think we want to get this into a polymer, which is a more friendly way to coat, energetics.
Thanks.
Yeah.
Have you or anyone looked at imprinting morphological memory on glass using a known polymorph in the presence of HF? We hear this anecdotal stuff about certain beakers that crystallize things as one or the other, and would like to exploit it.
All right. So when I went out in jobs in 1999, my proposal was to use molecular imprinting into polymers to do polymorph control. So I was going to take like libraries of inorganic crystals, imprint them into polymers, and then use those to do selective crystallization of polymorphs. The control reaction for that is just don't imprint. And that's where I stopped, because it already worked better than any other technique out there for polymorph discovery.
All right, we would like to once again thank Professor Matzger. So we have our cube that we give to all of our DLS speakers. So presented to Dr. Adam Matzger, with gratitude for your contribution as a distinguished lecturer. Thank you to your commitment to advancing innovation and the Navy TechConnect mission to connect ideas, technologies, and people in support of the warfighter. Thank you again.
Thank you.